Hey geometry students, how's it going? Got my nice Easter wear going on here and migraine's killing me, so hence the glasses. So sorry for the glare off the glasses. Overcast sky. We're going to talk about use geometric probability. Hopefully this will be a shorter one, but we'll see. Okay, so what is probability? It is how likely an event is going to occur. The equation for that is number of outcomes divided by number of outcomes in the sample space. Okay. I like to remember it as what I want divided by how many total there are. Okay, so let's talk about rain. Okay, so we've often heard like there's a 40% chance of rain. Okay, well 40% chance, and we know that probability hopefully can be represented not only just with, there's several ways we represent with the percentage. 40%, okay, 40%, cent, 100, okay, 40 over 100, okay, and we could certainly reduce this down and get 4 out of 10, and then reduce that down further and get 2 out of 5. So you can represent probability as a percentage, or you could represent probability as a fraction, and that's totally fine. You could also go 2 to 5. You could also do that. That's another way. But most often, probability is represented either as a percentage, a decimal, I could say 0.4 chance of rain, or as a fraction. Okay, so most often it's percentage or a fraction, and then sometimes a decimal. All right, so if we had a 40% chance of rain, that would obviously mean we'd have a 60% chance of it not raining. Okay, those are the only two options in this situation. Whereas, let's say we had baseball average of this, okay, a 0.300. We could also say he has a batting average of 300. Okay, well, how do we go from this to this? Okay, well, in baseball they often kind of convert it because they swing the bat so many times. They convert it to at bats. This would be 300 out of 1,000. So that means that this person is going to hit the ball 300 times out of 1,000 at-bats. Now, that sounds pretty terrible to you and I, but if you're a professional, that's pretty good, having a batting average of 300. Okay. Finally, the last one, dealing with cards, because maybe during this COVID time you're playing cards with your family and friends. We love to play hearts and spades and other games like that. So let's say that I was playing poker or something, or doing some gambling and trying to figure out how many cards, if I hadn't drawn any cards yet, and the first card I wanted to draw, let's say I wanted to draw an ace, okay? And I know that there are 4 aces, now throwing out jokers, 4 aces in a deck, then I know that the probability is 4 out of 52. The chances of me drawing an ace is 4 out of 52 cards. So 4 is what I want, or the outcomes in the event. There are 4 outcomes in the event. The number of outcomes in the sample space, there's 52 cards to choose from. Now, of course, we always reduce our fractions in math, so that means we have a 1 out of 13 chance of acquiring an ace out of a card. Okay, what is the decimal approximate on that? 1 divided by 13 is, that's about 7.7%. So 0.0 this, but so I rounded to 7.7%. So a 7.7% chance of drawing an ace. So I'm not going to talk about like if you were wanting to get a royal flush or something like that. That's beyond the scope for this one. How would be the probability of that? But you'll learn that later in pre-calc. So, but again, for right now, that's probability. So let's do one more real quick. What would be the probability of drawing a red card? Okay, well that's pretty easy. Red card. We could pretty much think of that. What's a red card? Okay, well, there are 2 suits of red, hearts and diamonds, and so there are 26 out of 52 red cards out of total cards, and so that, of course, we already knew the answer, but we know that there's 1 out of 2 chance of getting a red card. because the only other option is getting a black card, which would be the suits, spades, and clubs. Okay, so how does that apply to probability? Okay, let's deviate here. Let me set up a problem. Okay, so a quick sketch here. You're going to pretend that here I'm a regular hexagon here. So we're going to pretend, because clearly this length is not the same as the rest. But we're going to pretend, because my drawing skills are not the best this morning. All right, so what is the probability of actually it's afternoon, so probability of a random point lies in the shaded region, okay? So the easy part's the end part, but I'm going to go through, since this is good review for us to go back and figure out how to find the area of this region. All right, so we need to find the area of the shaded region, and we also have to find the total area. Those are the two requirements in order to do that. Because remember, we need to find the total and what I want. Okay, what I want is the area of the shaded region, and the total is the circle. Okay, in order to get the shaded region, though, I have to take the total minus the area of the hexagon. So we have a lot of things going on here, but let's just focus first in getting two areas: the areas of the hexagon and the area of the circle. Okay, I'm going to set those up. Okay, so the area of the circle is pretty easy. This is the radius, okay, because it goes all the way from the center of the circle to the outer edge. All right, so pi r squared, pretty easy. Plug and chug at 50.27 units squared. The area of the hexagon is 1/2 ANS. Okay, we don't know the apothem. We know the number of sides, it's a six-sided figure, and we don't know the side length. Okay, but we do know that we can find the central angle. 360 degrees divided by 6 is going to give me 60 degrees. Now, if you're really clever, you could realize that this central triangle here is an equilateral triangle. Okay, and then save you a lot of work. I'm going to go ahead and show the work if you hadn't known that. All right, so I'm going to take this image and replicate it down here. I've got this triangle. I draw my apothem, okay, and then I have x here, setting up here in reference to this angle. This is the adjacent side. This is a hypotenuse. So cosine of 30 is apothem divided by 4, or the adjacent side divided by 4. I guess adjacent and apothem here represent the same thing, but be careful with the variables. So a is 3.46. And then the next one is opposite angle 30, opposite over hypotenuse. So x is 2, okay? But I need the total side length, okay? So the total side length is going to be 4, okay? Total side length is going to be 4. So plugging those values in, okay, I get this. And also, it's a good idea to always think, does my answer make sense? If the area of the circle is 50.27 and the area of the hexagon is 41.52, it kind of makes sense because it's smaller than that, but it's still rather large. Okay, if I got something like 22 or something, I'm like, that doesn't look like half. So I may have done a calculation error. So always ask the question in math: does my answer make sense? Okay, so going up there. Area of the shaded region is area of the circle minus area of the hexagon. That's the hexagon signal. And there we go. Okay. Last step was asking for probability. Okay. Alright, so probability of a random point lies in the shaded region is going to be the area of the shaded region, alright, divided by the total area. 8.75. Actually, it's units. Let me put unit squared here. And you can see that the units cancel. Okay, so it is a good idea to have the units there and provide them, especially if it's like meter squared, but in probability the units will cancel. I end up getting 0.17, and so we know that that can be 17%. Okay, so let's see. Which would I rather, the decimal or this or a fraction? Percentage is fine. If you'd rather leave it like that, either one is fine. I really don't, unless otherwise specified, I really don't care. So let's try one more, and that's it. Okay, so very rough sketch here. All right, so you're standing out here or something, and you want to, this is a fountain, okay, and you've got a path around this, and you're here, and you want to just throw some rocks in the fountain because that sounds like fun. Okay, or maybe a pond. All right, so whatever this is, you're throwing rocks in it, and we want to know what's the probability of you throwing a rock into here, all right, and not landing out here. Okay, so this length is 30, this length to here is 40, so this length from there to there is 10, and the radius of this is 5. Okay, so let's do the setup. Okay, so I had to change something. I changed this to 15 because that wouldn't make sense. I had it originally as 10, but if that's 5 and that's 5, and if that's 5 and that's 5, how can that be 30 here? So this has to be 15 if it's half the distance. So change that to 15. Okay, so area of circle, pi r squared. All right, pi r squared, 78.54 feet. Area of total, I just cut this into a rectangle here, okay, and then a half circle. Okay, so area of the rectangle plus area of the half, big little big circle, so 30 by 40 plus 1/2 pi r squared. This is the radius there, plus plus plus, and adding all those, and so we are so close to being done. Putting those values in, area of the small circle divided by the total area. Units cancel, feet squared and feet squared. You get 0.050 dot dot dot. I didn't round, but now I did, and that comes to 5%. So you have a 5% chance of making the rock, or throwing the rock. Well, that's not basing on skill. What's the probability of the rock going in there? So negating skill, and maybe you guys can throw. You guys have seen me throw markers, so I have probably lower than 5% chance. All right, so. Again, may the Lord bless and keep you. Have a wonderful Easter, and yeah, just stay safe. All right. Okay.